Hello everyone, welcome today. Today we're going to do some of the hardest SAT math. Today's problem is based on geometry in SAT. We're gonna explore some of the areas in geometry to speed up our process to help us understand and then do the problem within the time frame so we have enough time in our SAT test to go and approach all of the problems. So let's begin. So here is the problem. We have three circles that are tangent to one another and has a radius of 1. So each circle has a radius of 1. So they are all congruent circle with radius 1, and this also has a radius of 1. And we are told to find the area of the shaded region surrounded by these three circles. So this is the area. That is what we need to find the area of the region, the shaded region of. So let's start. How do we start this? So first of all, problem like this, obviously it's a geometry problem, and it is very important to draw a figure that is convenient for us to further analyze this. So if you look at this, there is a symmetry. Three triangles are congruent and are connected. So each center, if you try to connect this each center, you'll nicely create a triangle, which is going to be an equilateral triangle. So basically, each angle in this triangle would be 60 degrees. So this angle is also 60 degrees. This is also 60 degrees. And we're gonna need that angle later on. So let's start formally. The easiest way to find this area is to look into this triangle. If you find the area of this triangle, it will be very easy for us to find the area of that region. So each angle here are 60 degrees. So let's say this is A, this is B, this is C. So area of an equilateral triangle is given by S square radical 3 over 4. And S is any given side of my triangle, and obviously this is equilateral triangle, so all of the length of these triangles are congruent. So I don't need to know if there are any other different sides. They're all the same sides, and the radius of these circles were 1. So if you connected these two centers, the effective area of one of these sides in this equilateral triangle will become 2. So if you plug in that 2 for your S in a formula, then it's going to look like this. So basically that 2 square will give you 4 times radical 3 divided by 4. 4 cancels. So radical 3 square unit, since we don't have any units. So that is my area of that triangle. Okay, so far we have the area of that triangle. So let's focus here. I do have the area of this triangle, and somehow if I also find area of this individual sector, this 60 degree sector, a piece of pie from this each circle, and add it up and subtract from that area of a triangle, I will have my area for the shaded region. So we need to find area of a sector. So let's find the area of that sector. So I have a circle with a radius 1 degrees, and this is radius 1. Sorry about that, not a degree, it's a length. And the angle is 60 degrees. So for a triangle A 360-degree triangle will have an area of pi r squared. So if for 1 degree, the triangle will have an area of pi r squared divided by 360 degrees. Because then you have to divide it by 360 degrees, meaning 360 different part, to get one part out of 360 degrees. But in our case, we are not looking for an area of 1 degrees. We are looking for an area of random angle, which is in my case theta. So if theta is what the angle of a sector is, the area of my sector will become pi r squared over 360 times theta. Okay, so in my case, my theta is 60 degrees. So pi r squared times 60 degrees over 360. Okay, so this is easy computations. This 0 can cross them effectively, and also 6 and 36 are easily divisible. There are 1 6 in 6, and there are 6 in 36. So my result would be pi r squared over 6 square unit. Okay, let's go back here. But the area that you just found is for 1 sector. I need to find area of 3 sector, because we have sector 1, sector 2, and sector 3. 1, 2, and 3. There are 3 sector. So nothing fancy. I already have the main area of total sector, the 1 sector, and I just need to multiply that with 3, because that's 3 times the single area. Just place 1 underneath, make it look like a fraction. So simply there are 1 3 in 3, and there are 2 3 in 6. So you get pi r squared over 2. So now is the easy part. Like we discussed before, if I have the area of a triangle and I have the area of my sectors, I just subtract the triangle area and with the area of a sector. So the shaded area is triangle area minus area of a sector, which is the total area, not the individual one. This one is the total area. So we already know the area of my triangle, which is here. So that is radical 3. And then we also know the area of a sector. So let's compute the actual area of my sector. What we have here is a generic formula, but in my case a radius is given. So pi, radius was 1, so 2, so it will be effective pi over 2. Okay, so pi over 2. Okay, so in my case, radical 3 minus pi over 2. Pi over 2 is a fraction. So let's make radical 3 also look like a fraction, so it's easier to see, easier to compute. And the common denominator in these two fractions will be 2. So in my case, I need to introduce 2 for this radical 3. So I do need to multiply 2 top and bottom. Effectively, I'm just multiplying by 1, but that will change my denominator to 2, make it easy for my computations. So my new number is 2 radical 3 over 3 minus pi over 2. And, oh, excuse me, this is 2. So it's 2 radical 3 minus pi over 2. And that is the area of shaded region. So this is my area of a shaded region. Okay, in SAT, it is important to keep track of your time. So we want to minimize as much time possible to squeeze time to do problems in a mandated time frame. So the time goes from 60 seconds to 70 seconds, sometimes 80 seconds, depending upon the difficulty level. This problem was difficulty level 5. So obviously, one thing you noticed, I didn't give you the answers for this, but they do have 4 answer choices. And there is a trick before you do this problem to all the way and find the answers, which is here. You can always use your tactics to eliminate your choices. So instead of working against 4 choices, you can also work against a minimal amount of choices, which would be 3 choices or 2 choices. And if you're able to cut down number of choices, chances of getting it right is higher. So these are the choices that was given for this problem. So let's explore what is going on here. Okay, so there are choice A, choice B, choice C, and choice D. Now you know our answer is choice D. But wouldn't that be awesome if you were to find this answer right away without even need to find any of this? So this is how you do it. By the time you come around pi r squared over 6, which is here, and then you will multiply pi r squared over 6 times 3, you will know pi over 2. So guess what? You have a fraction which is pi over 2 here, and you have another area which is radical 3. Somehow you subtract, you know your denominator has to be 2. Sorry, this would have been 3 and this would have been 3. Okay, has to be 2. So right away you can eliminate your choice B and you can eliminate your choice C because they don't have the denominator of 2. So you don't even need to know the top part is right or wrong. The bottom part is automatically wrong, so you just eliminate that choice. So you're effectively working against A and D. So that will give you a better edge on solving this problem right. So instead of working against 4 problems, now you're working against 2 problems. And this is how you can avoid spending more amount of time and actually use that time that you saved on each problem and to finish your problem earlier and use the extra time to go back and review so you have better chances of getting more marks out of that section. Okay, thank you for watching. I really hope you like this. I will be uploading series of videos on a hardest SAT math, on geometry and all other sections. Continue watching my channel and please don't forget to subscribe.